Chapter 22, Electronic and NMR Spectra of Molecules, Section 22.2, Electronic Transitions and Selection Rules. Any electronic transition that involves the change of the electron spin state is forbidden with nearly zero intensity because the integral of alpha star beta is zero. The integral of beta star alpha is also zero. Star denotes the complex conjugate, the intensity of a spin allowed transition, such as from alpha to alpha or from beta to beta in an atom or molecule, is proportional to the squared modulus of the transition dipole moment, which is a vector here, mu superscript mn with an arrow, and the intensity is proportional to squared modulus of this vector. We can prove this statement if you like to watch this 23-minute proof here in my YouTube channel. The transition dipole moment can be expressed as the sum of three components in the x, y, and z directions. I, j, k are the unit vectors in the x, y, and z directions, and then mu superscript mn sub x is the x component, y component, and z component here. Let's look at the x component of the transition dipole moment. It's the integral of the wave function of the mth electronic state multiplied by this x component of dipole moment multiplied by the wave function of the nth electronic state. So we can evaluate this mu sub x, mu sub y, mu sub z separately. And again, x, y, z are the x, y, z components. Over here, mu x, mu y, mu z are the components of the electric dipole moment expressed here. And with m and n in the superscript, it's the so-called transition dipole moment, which is also a three-dimensional vector with three components in the x, y, and z direction. An electronic transition is allowed only if this transition dipole moment is non-zero. As long as it's non-zero, its squared modulus is positive, and then we have a finite intensity to observe this transition. But if this is zero, then we say the electronic transition is forbidden. But how can we determine if the transition dipole moment is zero or non-zero? Well, we will have to evaluate three integrals, these three, the x, y, and z components of the transition dipole moment. If all three are zero, then the vector of transition dipole moment is zero. The electronic transition is going to be forbidden. If any one of these three integrals is non-zero, then the transition dipole moment vector is non-zero. We will be able to observe this transition as long as it's also spin allowed. The intensity of a spin allowed transition in an atom or molecule is proportional to the squared modulus of the transition dipole moment. Here's an example. If we're looking at the electronic transition from 1s alpha to 2s alpha in a hydrogen atom, this is going to be forbidden because its transition dipole moment is zero, the squared modulus is also zero. However, if you have an electronic transition from 1s alpha to 2px alpha, that's actually allowed, both spin allowed and spatial allowed. Now let's look at these two examples in detail. From 1s alpha to 2s alpha, it's spin allowed from alpha to alpha. Now let's look at the spatial intensity, spatial probability. So let's look at this x components. This is mu sub x with mn in the superscript. M and n represent the initial and final electronic state. So now let's plug in all those equations. C is a constant. Now we need to integrate this integral and also a spin integral. The spin integral is just 1 because the integral of alpha star alpha is just 1. Alpha is normalized. Really, we need to focus on this integral and see if this integral is 0 or non-zero. This integral is actually 0 because a 1s function and 2s function are even functions of x, and then in the middle we have an odd function of x. So if we look at the product, this entire product is an odd function of x. What does that mean? If we change the sign of x, we're going to change the sign of this product, and that means the integral is going to be 0. The integral of any odd function from negative infinity to positive infinity is 0, only because if you look at the graph of the integral, the left hand side and the right hand side have the same magnitudes but opposite signs, so overall the integral should be 0. And similarly, we can determine the y component and z component of the transition dipole moment. They are both 0. You just plug in y here. It's going to be an odd function of y. The integral of that product with respect to dy is 0. You can also replace this x with z to get the z component. Again, the integral of the product with respect to dz is going to be 0. So that's why we actually cannot observe the electronic transition from 1s alpha to 2s alpha if it's photon induced. Now let's look at this B from 1s alpha to 2px alpha. This electronic transition is allowed. This is because now we still look at this integral and multiply by the spin integral. The spin integral is just 1, so we focus on this spatial function. We look at here, we'll plug in all the wave functions over here and here. You can see this 1s wave function is a even function of x. That means when x changes sign, it does nothing to to this wave function. But this 2px is proportional to x. So therefore, 1s times x times 2px is together is a even function of x, and that means this integral is not going to be 0. Again, you can even just use a more specific function for 1s, it's e to the power of negative r, and then 2px is x times e to the power of negative r over 2. If you integrate this from negative infinity to positive infinity, I think you'll get a positive integral value. That means this x component is non-zero, and that means the transition dipole moment is non-zero. When the transition dipole moment is non-zero, its squared modulus is non-zero, and the intensity is proportional to this, and therefore the intensity of observing this 1s alpha to 2px alpha electronic transition is positive. We can observe this. This is an allowed transition. More generally speaking, the selection rule for the electronic transition in the hydrogen atom is delta L is plus minus 1. The angular quantum momentum number must change by 1. The intensity of a spin allowed transition in an atom or molecule is proportional to the transition dipole moment squared. For example, if we look at an electronic transition in water, the electronic transition from a A1 MO to a B1 MO is allowed, but from B1 to B2, that's forbidden, because we can actually look up the symmetry for x, y, and z vectors, because when you have an electric dipole moment, that's the charge times the x, y, z vector. So somehow we can determine the symmetry of the electronic dipole moment in the x, y, and z directions. Again, x, y, z, let's look it up. X is B1, y is B2, and z is A1. Therefore, x, y, z correspond to B1, B2, A1 irreducible representations. Now, in the x direction, the A1 to B1 electronic transition dipole moment is the integral of a totally symmetric function. So A1 times B1 times B1. All right. This is the initial initial electronic state. This is a final electronic state, and this is the x component of the electric dipole moment. So A1 times B1 is A1 is completely symmetrical, and the integral of a completely symmetrical function is non-zero. So the x component is non-zero. Therefore, the entire vector cannot be 0. The transition is allowed. However, from B1 to B2, it's completely forbidden, because none of the x, y, z vector has a A2 symmetry. We can see if you have B1 and B2 in the integral, this is initial, this is final electronic state. In the middle, we need a A2. We need a A2 so that the product is A1. So that integral of this product is non-zero. However, you can see A2 over here. Neither x or y or z correspond to this A2 symmetry. Therefore, the electronic transition from a B1 molecular orbital to a B2 molecular orbital in water is forbidden. In the x, y, and z direction, the B1 to B2 electronic transition dipole moment is an integral of B2, B1, and A1 function. We can do this here. Again, the transition is from B1 to B2. And then in the middle, we have the symmetry for the x vector, y vector, or z vector. They correspond to the symmetry of the electric dipole moment. And the x is B1, y is B2, and z is A1. So you can see when we do this product, we get B2. So B times B times B is B. All right, B corresponds to kind of just the anti-symmetric with respect to rotation. 1 and 2 are referring to symmetric versus anti-symmetric about reflection. So B, 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 you get a B. B, A, B, you get an A. Because B times B is A. And then, you get A over here. And then let's look at 1, 1, 2. 1 means symmetric, 2 means anti-symmetric. So you can replace 1 with plus 1, 2 with negative 1. So plus 1, negative 1. The product is negative 1. So we put a B here. Plus 1, minus 1, minus 1. So we put a 1 here. Plus 1, 2 means negative 1. So we have plus 1 times plus 1 plus times negative 1. We get a negative 1 here. So the result is B2 symmetry, B1 symmetry, A2 symmetry. None of these three is totally symmetric. So the integral of a B2 function is going to be 0. The integral of a B1 function is 0. The integral of A2 function is also 0. That means the x component, y component, and z component, they're all 0. The transition dipole moment factor has to be 0 if its three components are all 0. Therefore, B1 to B2 electronic transition in water is forbidden. And not only in water, just in any molecule with the C2V point group, the B1 to B2 electronic transition is forbidden. Using the character table, we can also determine if a vibrational transition is infrared allowed or Raman allowed. For example, we can look at the symmetry of the vibrational modes. The A1, B1, B2 vibrational modes are infrared allowed in any molecule that belongs to the C2V group. Because you can look up the three electric dipole moment in the x, y, and z direction. X is B1, y is B2, and z is A1. So you just need A1 vibration mode to be allowed in the z direction. B1, look up B1. Then this is going to be allowed in the x direction, and also there's a B2. You see B2 here. This vibration will be allowed in the y direction. Alright, so this is how we determine if a vibrational transition is infrared allowed. Again, this molecule absorbs a photon and it can be excited or de-excited as long as it's infrared allowed. To determine whether it's infrared allowed, you need to look up the symmetry of x, y, and z. They correspond to the symmetry of the electric dipole moment. So if you have B1, B2, or A1 symmetry, it's gonna be allowed. All vibrational modes of a molecule in a C2V point group are Raman allowed, because for this to be Raman allowed, you need a vibrational mode with the same symmetry as one of this, either x squared or y squared or z squared or x, y, y, z, zx. You can see x squared, y squared, z squared, those are A1, x, y is A2, x, z is B1, y, z is B2. So pretty much no matter what you have, if you have A1, A2, B1, or B2, it's going to be Raman allowed. To check if it's Raman allowed or forbidden, you look for the second order functions such as x squared, y squared, z squared, or xy, xz, yz. You look for them and see if they are allowed or not. When a molecule possesses a inversion center, x, y, z are always U symmetry, while the components in the polarizability matrix are always G symmetry. Alright, so when you have an inversion center, x, y, z are always anti-symmetric with respect to the center. However, if you're looking at the second order functions, they are symmetric. with respect to the inversion center. So what does that mean? Well, as long as you have a molecule with a inversion center, XYZ will always be U symmetry, and all those second order functions will always be G symmetry. What does that mean? That means we can make a prediction: no vibration mode of a molecule with a symmetry center or inversion center can be both infrared and Raman active. If it's infrared active, it's definitely Raman inactive. If a vibration mode is Raman active, that means it has a G symmetry. It cannot be infrared active. But also, I just want to remind you that one infrared vibration mode can be both infrared inactive and also Raman inactive. Alright, so over here it's just infrared and Raman cannot be both active if you have a molecule with a center, inversion center. The intensity of a spin allowed transitioning molecule not only depends on the value of the squared modulus of the transition dipole moment, it also depends on the overlap between the vibrational wave functions of the initial and final electronic state. The Frank Condon principle states that the electronic transitions are vertical transitions. What does that mean? That means, well, in a potential energy surface, when we do electronic transition, we draw the arrow up perpendicular to the horizontal axis, which is the nucleus coordinates. And simply it means the nuclear coordinates remain unchanged. When you draw a vertical line, that means over here, the positions remain unchanged. Why is that? It's just because the electronic transition is super fast. It takes about 10 to the power of negative 15 seconds. I think this is 1 femtosecond. And within such a short time period, all those nuclei do not have enough time to move. I mean, even if they do, they can move maybe a distance of maybe 1 picometer or even less. 1 picometer is 0.01 angstrom. So typically the bond distance is between 1 and 3 angstroms. And if you just change it by 0.01 angstrom, roughly we can say, well, the bond distance is unchanged. And now let's look at some vertical excitations. Let's say we have ground electronic state, and this is also the ground vibrational state with a wave function. Now we're going to do vertical excitation. So from here to here, not only we need to look at the transition dipole moment, we need to look at the overlap between this vibration wave function and this vibration wave function. So you can see we are from this really large value of vibrational function to a large vibrational function here. This is the maximum of a Gaussian function. This is also a maximum of a Gaussian function right here. So very likely from 0 to 2 transition, you will have a larger intensity than any other intensities. Alright, and now let's look at examining from 0 to 0. Well, this from 0 to 0, you need the least amount of energy, but look at the overlap. Over here you have a maximum, but over here very low intensity from the vibrational wave function. Alright, so that's why the intensity should be small. From 0 to 1, it's also small because if you look at this, this is quite close to the tail of this Gaussian function, so not much. But from 0 to 2 in this graph, you can see this is the maximum of this Gaussian function, and this is the maximum of this Gaussian function. So from 0 to 2, you probably will see the largest intensity for this electronic transition. Again, the transition intensity is not only proportional to the squared modulus of the transition dipole moment, it also is proportional to the squared modulus of the overlap between the initial vibrational function and the final vibrational function. That's why the transition is like that. So when you look at this kind of transitions, in this diagram I said from 0 to 2, you have the largest overlap between this vibrational function and this vibrational function. So from 0 to 2, you probably will see a larger transition intensity.